Hello everyone, welcome to Crypto Innovation Webinar Interview Series. I'm your host Shravani. Today we are in season 4 and part 1. The topic is very interesting, a science of security, the long road ahead. A digital technology races ahead. We have been witnessing an increasing number of security issues that it entails, and yet more are sure to surface. Systematically understanding and addressing such issues remains an open and evolving challenge. In this talk, we speculate on what a science of security should involve, drawing up on our learning from theoretical cryptography. And to discuss this, we have with us Professor Manoj Prabhakaran. Before starting the discussion, let me introduce Professor Manoj. Manoj Prabhakaran is the Vijay and Sita Vashee Chair Professor in Department of Computer Science and Engineering at Indian Institute of Technology, Bombay. His research interests span theoretical cryptography, information security, and various topics in theoretical computer science and information theory. Prior to joining IIT Bombay, he was associate professor of computer science in the University of Illinois Urbana-Champaign from 2005 to 2016. He received a PhD in computer science from Princeton University in 2005. Manoj graduated from IIT Bombay in 2000 with BTech in computer science and engineering and the Institute Gold Medal. He has received an IBM PhD fellowship, an NSF Career Award, a Beckman Faculty Fellowship, and Ramanujan Fellowship. He is an associate editor of the Journal of Cryptology and a member of steering committees for the Theory of Cryptography Conference and the Information Theoretic Cryptography Conference. Welcome, Professor Manoj, to Crypto Innovation Series, and stage is all yours, sir.
Thanks a lot. Thanks for inviting me for the talk, and thanks to everyone for taking off your time to attend this. So this is as I was suggesting in the synopsis that was read out, it is a speculative talk, and I do have various thoughts over the years on what a broader notion of science of security should be. I work in a particular corner of this, right, theoretical cryptography, but there's much more to security than cryptography. So these are a few of those thoughts, by no means meant to be complete or exhaustive. And there's a first iteration of this talk, so we'll see how it goes. All right, so trying to get a sense of what a science should be, right? Going back to the basics, and what all should it cover. And at a very high level, there are kind of two parts to something like this, right? You'd want to know, you'd want to answer questions of what and how. And so it's not just what is security. We also are interested in defining security of what, and that's a very non-trivial question, as we shall see. Both of these are what is security, whose security are we talking about? So whatever the answer should be, that should be part of what the science should do, what new science should do. Okay, so let me, with that, launch into my speculation. I'll start with a look back at encryption. That's where I come from, theoretical cryptography, and kind of see, if we can draw some lessons from how the science of cryptography, as it were, evolved. Okay, so people have been using encryption forever, right? For centuries or even millennia, and so when people started using it, they didn't try to formally define what encryption is doing. Just something useful to, in particular context, and you just start coming up with techniques for doing it. And there were all these Skytail or CIS cipher. Edgar Allan Poe is an interesting character as a poet, but he also, was kind of into solving puzzles and what are called cryptograms. So this is all kind of popular science, kind of, or rather popular kind of culture ways of thinking of cryptography. And of course, there's also military or political angle to how cryptography developed. things like CIS cipher or the ciphers that were developed during the World Wars, and all the way to, in the 70s, we had things like what's called the DES, the data encryption standard, and of course it's continuing to grow, right? So these are all questions of what or rather what how to do cryptography, how to do encryption. This, for those of you who are familiar with it, these all of these examples I have here fit into what's called symmetric key encryption. And a big breakthrough in this whole way of doing cryptography was the innovation of public key encryption, public key cryptography more generally. And some of the people involved, Diffie and Hellman and Merkel, and RSA, Russian Redden. There are many Turing Awards that have been won for important work in cryptography. And so this is all very important, great steps ahead in the history of encryption and cryptography more generally. However, we didn't quite have a mathematical definition of what encryption is doing. And everything was based on kind of an intuitive idea of what encryption should be. So the formalization of what encryption is actually followed much later. It came, so it's not centuries or millennia old, it's just decades old, okay? And the first such instance of a formal definition, an attempt at a formal definition, was by Shannon. For those of you who know or don't know, Shannon is the kind of the founder, as it were, of the whole field of information theory. He doesn't have a Turing Award, but he is like the Turing for information himself. So in the 40s, Shannon came up with this, seminal ideas of how to measure information, how to talk about communication, and also how to measure secrecy. Right? So he had a very simple model. So pretty straightforward block diagram there of an encryption and a decryption algorithm with a eavesdropper on the channel and so forth. And he could formalize what it means to prevent the eavesdropper from getting information. Okay, but this was in the 40s, and well before the kind of say public key encryption was there, right? So the real kind of start of modern cryptography was in the late 70s or early 80s. Of course, Diffie Hellman and RSA were all kind of the turning points in that evolution. But the real definition of what security of encryption is was by Shafi Goldwasser and Silvio Micali, who also won Turing Award about a decade back. And that they were building on top of, at that time, a very new kind of way of connecting computational complexity with cryptography. And they had a definition of what it means to be a secure encryption. And of course, the techniques of how to do cryptography, how to do encryption, how to build other things, it continued. They were, not immediately probably affected by the definitions, but certainly, over time, by now, we do go back to these definitions to see if new constructions, whether it's in elliptical cryptography or block ciphers and hash functions, whether they fit these definitions we are trying to, or that we have put down. Okay, so the definitions are not just for encryption. There are various other things in cryptography, signatures, message authentication, and so forth. Then, all of these have security definitions now, which are in the spirit of what Shafi and Silvio came up with in the early 80s. So you might wonder, why am I making a big deal out of defining? What is there to define in security of encryption? Can't we just say that, and so look at the block diagram that Shannon had, and just say, eavesdropper shouldn't get any information about the message. Right? And to some extent, that's a good starting point. But even for this, you need to say, what does it mean to get some information about a message? What is information? And this is precisely what Shannon was doing. There's a tool that he was developing to measure information. In this case, of course, you wanted to say the eavesdropper gets very little or zero information, so you don't need all the power of Shannon's toolkit, like entropy and mutual information and so forth. But the bottom line is you need to define, you need to mathematically formulate what information is before you can have a formal definition of a security of an encryption scheme. Okay. Unfortunately, incidentally, once Shannon put this definition down, he could prove that you cannot really do a lot of, you cannot do much about achieving this definition. This definition is quite strong. Okay, that's how I'd like our definitions for security to be. They should be quite strong. But what he showed is that you can essentially do only what's called one-time pads. If you want to encrypt a lot of messages, you need kind of fresh key as long as the message is. Okay, you cannot reuse a short key over and over again, and that's a key that is shared between the sender and the receiver, symmetric key setting. And the public key setting, he didn't come up with anything because it was just impossible, right? You could show that you need to share. A consequence of saying that the only way you can do encryption is if the sender and the receiver have shared this key, which is as long as the message, is to completely rule out public key encryption where there is no such shared key. Okay, so this is of course not good enough for us today, right? This is not what we want from encryption. So so we need to change this definition. And this is a recurring theme when we try to formalize various security definitions in cryptography, that the simplest, most natural way, the most convincing definition of security may be a little too strong. It may be unattainably strong. And then you have to go back and weaken your definition, which would mean you have to kind of make it more complicated, allow some sort of some ways in which information is leaking or something, right? So in this context, you need to settle for a more complex definition. And so in this context, what that meant is that you cannot ask for the eavesdropper not getting any information about the message being sent. If you are going to reuse a key, like Shannon said, you will leak some information. But you would be happy as long as this information that's leaked to the adversary is inaccessible in some sense. It's hard to access. Okay, so it's not that the adversary's view doesn't contain the information about the message. It's just sitting there in a way that, in some sense, hard to use. Okay, but then it should be clear that that's even harder to define. It is already a little tricky to say what does it mean for the adversary not to get any information. But I told you, it turns out to be fine. It's not particularly complicated definition. I probably do spend a lecture, in a course, motivating that simple definition, but it's simple enough. However, this thing saying that the information is actually there, but you cannot get your hands on it, that's a much more delicate thing to define. And that's what we, in the late 70s, that's what we managed to define using notions of computational hardness or computational complexity. Okay, so I'm not going to, there's not a technical talk. I'm just trying to keep things as at a high level. So I'm not going to the exact definition. Suffice to say, there is a definition. But once you have that definition, so this is what you could think of what Silvio and Shafi had. They were, of course, building on top of other definitions for notions like pseudo-randomness that were before that. But once you have this definition, how do you achieve it? The whole point of coming up with this complicated definition is to be able to achieve it. But there's one more hurdle to achieving this, which is that it relies on computational hardness. And unfortunately, we don't know how to prove that there are problems that are actually computationally hard. Okay, so there are a lot of conjectured problems saying that this problem has a certain kind of computational hardness that will make it suitable for various cryptographic constructions, but we don't have a proof. There are wide, fundamental, long-standing problems in computational complexity. You might have heard of P versus NP, which are completely open. And unless we can resolve them and go well beyond that, we cannot hope to prove that various problems are computationally hard in the way we want it. So we had to settle for conjectures. So these are, as I'm saying, they're mathematical conjectures, right? They're saying this problem is hard. That's the nature of the problem. It's not a conjecture about, there are no people clever enough out there who can find an algorithm for this. The conjecture is that these problems do not have algorithms that run fast enough and solve it. So based on such assumptions about their mathematical assumptions, assumptions about nature, if you will. But if those assumptions are true, they're widely believed assumptions, and assuming they're true, then we actually prove that what we would like to do is prove that here is a construction which is secure. It's not that there is nobody clever enough out there to break this crypto system, but there isn't a break. Okay? You can prove that there are no attacks, that there doesn't exist any attack. Attack according to the security definition that we have. Okay, so that's kind of how pretty much all the definitions in modern cryptography go. In the case of encryption, what Goldwasser and Vitali gave, they call it semantic security. Now, you would probably come across it more commonly under the name of security against chosen plain text attack. And it's a beautiful definition, right? It covers a lot of things that you may not think of. In fact, the questions that people before them didn't quite think of explicitly. For instance, suppose somebody encrypts the same message twice. Should the eavesdropper learn that they actually encrypted the same message twice? The eavesdropper doesn't learn what the message is, but the eavesdropper shouldn't be able to tell that these are actually the same message. Okay, that's a reasonable requirement to make of an encryption algorithm. Another thing is, what if the eavesdropper has a guess? They think that you are saying hello. Okay, so a message went past from Alice to Bob. It was encrypted, and if the eavesdropper thinks, okay, that must be a hello. Let me check if it's a hello. We want to make sure, we want to say, look, the eavesdropper shouldn't be able to check if it's a hello. All that the eavesdropper should know is that some message was sent. That's something we cannot quite hide. That a communication happened, at least in the model that we have, where there's a line going from Alice to Bob, and the eavesdropper has access to it. So the eavesdropper will see that a message went by, but beyond that, it should have no idea. It shouldn't be able to check if it is a hello or not. Okay. In fact, the eavesdropper might even be able to influence the messages that Alice is sending to Bob. The eavesdropper might go and tell Alice, please send your date of birth to Bob, right? So, and then she just waits to see what's going on through the channel, and she doesn't probably know exactly what the message is, but she has good control over what kind of message is being sent. So the eavesdropper might influence the message that's going on, and that's a name, the chosen plain text attack. The message, the plain text, could be chosen by an aggressor. Okay, so it's a beautiful definition that, without having to spell out each of these various considerations, handles them all. And in particular, what was considered an encryption by RSA, Reversion and Edelman, it turns out not to meet any of these security guidelines. It's a deterministic algorithm, which once you fix a key and the message, it keeps outputting the same ciphertext. So you can tell it's a public key encryption. You can guess the message, encrypt, check, compare it with the message that's going wrong. So it kind of completely fails this notion of security against chosen plain text attack. And you might wonder, clearly, RSA are very clever people, how could they have missed this, right? And that's because they were not planning to achieve this definition or any definition for that matter. They had an intuitive idea of certain kind of computational hardness that needs to be achieved, and the RSA function, is something they came up with, which has that kind of hardness. Today, we would call such a function a trapdoor function or a trapdoor permutation. But it's not good directly for encryption itself. So it was sometimes called the textbook RSA. So don't use the textbook RSA for as an encryption algorithm. So this, is a risk of doing things before knowing what you want them to be like. So you're doing how before what. Of course, it's good that RSA is doing how before, without waiting for what. In fact, the answer to what wouldn't have come out unless RSA had put out this algorithm or Diffie-Hellman had put out this algorithm saying, look, here is something interesting we can do. And then others are sitting down and trying to figure out, okay, what is this interesting thing that it is doing, right? So, of course, I'm not saying we had to reverse the order of things, but when once you come up with the definition, you will probably need to go back to what you were doing, and then you'll sometimes realize that it is not quite doing what it should have been. And that's also there in various other legacy cryptographic things out there where people still say something like, so the CBC mode of encryption for this. By now, there's no particular reason you would want to use that for encryption. You would use a counter mode. But when this particular mode was developed in the 70s, there was no notion of what it is trying to achieve. So you didn't realize that something much simpler like the counter mode would actually work. Okay, so just if you don't know what CBC mode and counter mode are, it doesn't matter. All right, so okay, so that is great. That's a good story. Goldos and Mikhail came up with this definition, cleaned up the whole thing. But it turns out their definition is not strong enough either. Okay, and that's another recurring theme. You start with something simple. It was too strong. You have to make the definition more complicated so that now it is achievable. But you might have made it a little too weak. So it's achievable, but it's not good enough. And then you might need to make the definition even more complicated so that it's achievable and it is useful. And how useful it is actually, it's not easy to see until you have a big picture of where you're going to use this encryption or the cryptographic primitive, where it fits into a bigger picture. It's not clear if it is too weak or good enough. So it turns out this CPA security, chosen plain text attack experience, chosen plain text attack, was not strong enough. So just for fun, I just borrowed a slide from my lectures on encryption, just to kind of show you a picture, right? Show you an attack to make it kind of concrete, what is there beyond chosen plain text attack that you might want from an encryption scheme. Okay, so imagine there is there is Alice and Bob, and Alice has some little poem she wants to send to Bob, and sure enough, she can encrypt it. So so she encrypts it for Bob. So I'm not showing all these things here. She's using the public key for Bob. She is using some randomness to run the encryption algorithm. And she ends up with a ciphertext, right, which is this envelope with the message sitting inside. And she can send it to Bob. Only Bob can open the envelope and read the message. Okay, so first so good. But of course, there is an Eve on the line. She is very curious what's in the envelope, but she cannot decrypt it. Right? That's what the chosen plain text attack security would give you. But she happened, she wouldn't give up so quickly. So she happens to be a hacker. She would hack at the message and come up with something else. She has, again, no idea what exactly it is because she doesn't know what exactly is inside this envelope. but she managed to come up with some encryption of a related message M star. This is original message is M. She does some operation on the ciphertext, comes up with a new ciphertext. She knows, let's say she knows that the M star is actually the same message M, but reversed, okay? But she has no idea what M star is or what M is. And she can send this new ciphertext to Bob, okay? But so what, right? She still doesn't know what is in what the poem is. So it seems like we shouldn't be worried about this. Yeah, but this public key encryption setting, which means Bob has published his public key and he is willing to get messages from any number of people. So Eve is an old friend. She has sent him something. He will decrypt it, and he will see that there is some sort of gibberish inside that. Okay, so there's actually the original message in the reverse. But since he doesn't see what's going on, he might just write back to Eve saying, "Hey, what is this thing that you sent?" Okay? And quote the decrypted message. And now, sure enough, Eve can reverse this and get back the message, which, so she never really broke the security of the encryption scheme, really, right? She just, only thing she managed to do on the ciphertext is garbled it so that it became a ciphertext of another thing. And that's, you would think, okay, why do you want to blame the encryption scheme for that? The encryption scheme never promised security, or it has nothing to do with this kind of hacked messages, right? But the point is, there's actually a real problem. This, if this were an ideal secure channel between Alice and Bob, and even if we let it reveal to Eve that a message went along and this is how long the message is, Eve shouldn't have been able to launch this attack in that kind of an ideal setting. And now here she is. She may be able to, right? So of course you might wonder, is this possible that she'll be able to do the hacking? It could be possible. The point is, it's not ruled out. In particular, if the encryption scheme encrypts character by character, this would become trivial to do, right? So what this shows is that, okay, there is a security concern that was not captured in CPA security, Chosen Security Against Chosen's plain text attack, and that's called Security Against Chosen Ciphertext. So, this was recognized. People have devised encryption schemes that are secure against this attack. But now you might start wondering, is there more, right? Do we need the security definition to be even stronger? And it turns out the answer is it depends. For specific purposes, for instance, if you're doing, and if you're using encryption in protocol like TLS for forward secure, setting up a channel with forward secrecy, it turns out even CPA security is good enough. You will always create a fresh key for each session, and there won't be a concern of this kind of email attack that I was talking about. But if you're using it for emails, then yeah, you might want CCA security. You'll have to exactly define what you want security to be for your higher level application, the email application. But CCA security is often good enough, right, depending on how you define things. But there are other scenarios where, so encryption is something so kind of general purpose that you would think, you would want to use it. You may not be a cryptographer. You're an end user of encryption, and you would want to use encryption in clever ways that you come up with, right, in your high-level application. And public key encryption should support that. So in that case, your mental model of what encryption is giving you may not match the exact security definition that CCA security is giving you. And therefore, over time, and there are a lot of other things that you might do which explicitly are kind of known to be a bad idea in the cryptography literature. Things like key cycles, for instance, if you encrypt a secret key of an encryption scheme using that encryption scheme itself, all guarantees are off. But as somebody who is thinking of encryption as this ideal black box, you cannot be faulted for doing it, right? So when you want to use encryption outside of the context of carefully analyzed protocols for your own purposes, then there are a lot of pitfalls. And the problem is, what you have in mind is a very idealized model of what encryption should give you. And there's a big gap between that and what the real security definitions give you. Now, over time, many of these things have been addressed and it's still ongoing. So various new notions of security have been added on to encryption, to public key encryption, say. So here, the security against chosen objects attack is something you will not find anywhere right now because it's just some work we have recently done. But that's one among several other works which have been adding additional security guarantees to public encryption. Okay, so the bottom line is, there is a lot to define, and the security guarantees, the devil is in the detail, and you think of it as a nice black box that you could use. Unfortunately, that is not the case. Okay, so you might even wonder, do cryptographers, when do we stop, right? Like we keep working on newer and newer, we're just uncovering more and more issues with even something as basic as encryption. So it's not all that gloomy. In theoretical cryptography, we do have some very powerful ways of modeling security that captures quite a bit of concerns without having to explicitly model them. So I mentioned Goldos-Mikaeli definition, they didn't explicitly model a bunch of things, it automatically handled a few things. And that has been kind of taken to a kind of a higher level, right? And that is this, what's called the real ideal paradigm of security definitions. And I'm not going to give the actual framework of the definition, but at a very high level, what is it doing? So the key to defining security is setting down what is the ideal security you want. Okay, so what is the functionality you want? In the case of something like encryption, you may define it as a secure communication channel, but that may not be good enough if you're trying to do something like disk encryption, right? You really want the ciphertext in your hand. You might want to do further processing with the ciphertext. So it may or may not be suitable for all scenarios, but whatever is your goal, whatever is the functionality you want to define, first define an ideal model for that. So again, I'm not going to the definition of how that would look like, but in the case of encryption, it would think of it as Alice and Bob connected with a channel which leaks to everyone else, to the outside world. It leaks the size of the messages that go through it, right? And then you compare that with the actual real world. What do I mean by real world? The scheme. The scheme is where you're using an encryption algorithm. You're generating keys, posting your public key, then getting messages, producing the public key and so forth, and decrypting it. So the whole, real execution, right? And then the security definition basically is the following. You'd consider your real scheme, secure, or a secure realization of this ideal if the following holds. Whatever could go wrong in the real world, if it could have already gone wrong in the ideal world, then it's not the fault of your encryption algorithm or the cryptographic scheme. It's a fault of how the scheme is used. Okay, so again, this may be the first time you see it. You would have expected probably a definition which would say the real world is as good as the ideal and nothing goes wrong in the ideal. actual definition is a little different. It says real world is as good as the ideal. Whatever goes wrong in the real world could have already gone wrong in the ideal world. Okay, so the ideal itself is not really ideal. Things can go wrong in the ideal world. Okay, and I'll come back to that later. But the point is, that's how it should be. We cannot give absolute guarantees. We cannot say, use my encryption scheme, nothing bad will ever come to you. No, what we are saying is that use my encryption scheme, it's as good as using the ideal channel. Now, even when you're using the ideal channel, things can go wrong, but don't blame me for that. Okay? So those are the kind of relative guarantees that these definitions give. And now, you can kind of look at the real and ideal, and um, you know, if you looked at what the CPA security corresponds to, you would see, okay, there is this missing part in the real world. You need to add a little more to the real world. And when you add that, you'll get CCA security and so on. Okay? So it's not quite like, we are magically pulling out more and more concerns. The concerns are kind of there, and it's like, okay, originally we chose to ignore it, and now, let's expand our model to include that also. Okay, I mean, that's kind of in hindsight, but you could think of that as what's happening. Okay, so that's kind of the real ideal paradigm. It's a really powerful way of going about security definitions in cryptography. It's not just for secure communication. It works beautifully for complicated things like secure computation involving multiple parties. When it's not at all clear, what should it mean to, say you're doing a database lookup, it's not clear what, so you don't trust the other side. Both parties don't trust each other. Database doesn't trust the client who's looking it up. The client doesn't trust the database, so the client doesn't want to just send its query to the database. And so it's not clear, what are you hiding from whom? The client should get the answer, but the server shouldn't see the query, but also the client shouldn't find answer to other queries other than the one he or she is making. So it's a very delicate, security requirement, and it turns out in the real ideal paradigm, you can kind of naturally give this definition. Okay, so it's a very, very useful model. But actually, what I wanted to say today is that it's not good enough. So the problem is, so in this, what I was saying earlier, the ideal, you may feel like, okay, the ideal is not ideal enough. Okay, that's fine. That's all we can get. Then we work with that. But the problem, the real kind of the weakness of the security definition is that the real is not really real. So what we cryptographers call a real model in this context is actually a stylized model of how you would be running your encryption algorithm. So you would have a Turing machine or an ideal computer on which you do various computation. You have ideal randomness, and you don't have any timing differences in when you encrypt one message or another message, and so forth, right? So it'll be all kind of a bare bones mathematical model. Computation is just applying a function. There are no side effects of that computation. So that's what our real model is. And that's not really real. That's not real enough. The actual real world is a much messier real world. Okay, and that's kind of the first kind of going beyond what cryptography or what theoretical cryptography deals with. You want to go towards a science of security, broader notion of security, then that's kind of the first glaring gap between the cryptographer's real world and the real world. Okay, so it's a big mess out there. There can be bugs happen all the time. There can be even problems in the way that protocols are designed. So these are not errors in the cryptography itself. It's not like some mathematician made a claim the wrong proof or anything. It's like some oversight in how things were designed. some legacy issues, how they were handled, some typo in a code, whatever, right? So there are, these are all names that you would come across over the last several years about attacks on mostly on protocols like the internet protocol, TLS protocols. And you'd also come across backdoors. These were inserted presumably by agencies like the NSA in the US, for instance. And that can happen in the real world. In our idealized model, we don't worry about these side channels. That's a big problem, right? So, a Turing machine or a function that has no side effects is not a good model of what happens in your computer, where the operating system, the hardware, everything is designed towards getting maximum performance out. You have caches, you have threading, hyper-threading. So, there are a lot of side effects that there's speculative execution that the Spectre and Meltdown were all about. So the real life is much more complicated. And then there is malware. Pegasus, many of you might know, is this WhatsApp malware commercially available, used by governments, and it has real consequences, right? It manages to, WhatsApp being popular as it is, it has a real impact in real life. This ANT catalog is a catalog of vulnerabilities and toolkits that NSA has developed in the US, and because this was classified until it was all got leaked at some point. Digital forensics is something that is not possible in an ideal world. I delete data, it is gone, but in real life, your hard disk, the magnetic surface of your hard disk might still have a signal about deleted data, right? So these are all kind of non-ideal nature of computation of real life that we ignore in cryptography. And to the credit of cryptography or cryptographers, this is Edward Snowden, who revealed a lot of information we know about how NSA works. So he said, properly implemented strong crypto systems are one of the few things that you can rely on. Unfortunately, endpoint security is so terrifically weak that the adversary can frequently find ways around the crypto. Right? So this endpoint security is what Pegasus or Spectre, Meltdown, they're all doing. They get into your endpoint, your computer, and ideally they shouldn't be able to get into your computer, right? And but they can through all these multiple ways. So that's a mess, and how do we fix it? And so, if it's a science of security worth its name, it should address this question rather than say it's not our problem. Right? It is our problem. And what the way I would look at it from kind of building on this little that we already have in cryptography, the real and ideal. What we really need to do is handle this mess, right? And in some sense, we already do handle this mess. It's not like the science is wrong, right? The cryptography said, oh, there is no attack, but there is an attack. No, that's not quite true. What we said is that, look, if your real model is like the real model we are imagining it is, then I can give you certain guarantees that will hold in this ideal world. But if your computational model deviates from this real model I'm imagining, then I will consider you a corrupt party. Okay, so that's what in cryptography we do. If you're not following the protocol the way we designed it, for whatever reason, it may not be intentionally, it may not be because you're malicious, you're a bad person, but for whatever reason, if you're not following the real model protocol the way we designed it, then we will say all bets are off. You get no security. We consider you as part of the attacker. You're colluding with the adversary. Okay, so we don't need to give you any more security guarantees. So that's what we do. So it's not that one way to put it is that it's not that the cryptographers were wrong. It's just that they didn't care about uh, this situation where most of us in real life actually find ourselves, right? When you have an app in your phone or in your device, it's far from an ideal computational model. You have this multiple other apps running around it, lots of data leaking across different apps, so a lot of side channels. So at this, taken literally, this would mean everyone out there pretty much would be considered corrupt, and we don't need to give anybody any security guarantees. Okay, so can we do better? Okay, that's not quite good enough. So often, I mean, in practice, of course, it's reasonably good enough because even though anybody is vulnerable to all these attacks like Pegasus and stuff, most people are not necessarily under attack at any point, right? So for them, these security guarantees do translate to things, meaningful things, but it kind of leaves everybody vulnerable. So can we do better? And I think there are two ways to think about bridging this gap. And let me go through both of them. So first one is somehow um, helping you, you're take your compromised device or bad computational environment and run enough protocols or whatever on it so that it starts looking like the real model that we wanted, right? This kind of idealized real model that we wanted. So let me start with that. So we would like to help with meeting these real model assumptions. And so for that, what we need is, so I put this arrow here. You have to kind of have exactly the same thing we did from going from this real to this ideal, right? You're actually running some complicated encryption algorithm, which uses whatever, right? Factorization, discrete log, whatever. It works over. It doesn't do anything that's actually like a clean, send a message through an ideal secure channel. There is no ideal secure channel here. But then we said, okay, run all our algorithms, and now you can pretend that you're living here. It gets as good as living here, right? That's what cryptography was doing. Now we will need that kind of guarantee from all these other things that take your phone and give you this model of computation on which all these apps are living, right? Saying that, okay, you will get your time to compute, you'll get your memory that you can use, nobody else will see, and you will have access to input output, nobody else will be able to see. So if you could provide that uh, abstraction on top of this real messy world, then we are good. And that would be the job of all the underlying layers, programming languages, operating systems, computer architecture, and even device physics. You're trying to say, you shouldn't leak electromagnetic signals that somebody can put an antenna and catch, right? That'll tell them what your key is. So you need security guarantees from all these layers so that, and they will do something non-trivial so that you can now be guaranteed that it's as good as living in this idealized real model. Okay. And it's not like, these branches of computer science don't do anything about it. They already have their own notions of security. They already do various things to prevent operating systems. You don't want one user to read another user's file system, right? Programming languages, you care about type safety. You don't want a bug that'll just, go uncaught by a compiler. So there are various safeguards that have been put in place by these in each of these disciplines. But this is where, I think we need to change our outlook a little bit. So what they're doing is the how part. Okay, there are a lot of techniques, and they're very useful techniques. That's like RSA, came up with this very brilliant idea of Diffie-Hellman came with this very brilliant idea of public key cryptography that works, almost works, but it doesn't plug into the next level of things properly. Okay, so they all have their own notions of taking their messy model and making it a little better, a little more idealized. But they don't compose with each other. They don't use the same language of what kind of security guarantee they're giving. In fact, they don't, as far as I know, there's no overarching notion of a way of defining security, right? So there's no what, and that's what we need to work on, right? Also, kind of make sure they talk to each other, they can be composed with each other, so that this one arrow that I was, hoping we'll be able to put in will actually probably be in the form of, putting together all these tricks and ideas from programming languages, operating systems, all of them, but in a way that one builds on top of the other, or they can work together and work towards this one goal of giving us this idealized real computation platform. So currently, that's not their focus, right? Even when you have something like security as a consideration, the primary goal in each of these areas is very different. They are mostly after efficiency. They cannot, often live with the overheads that'll come in if they try to make it very secure. You don't hear anybody talking about giving up on speculative execution, even though that's a root of many of these causes, root cause of many of these attacks like Spectre. What you're trying to do is, okay, let's make it a little better. Okay, so the first step in handling this mess would be to somehow change this outlook so that they're all working towards building this real model that then higher layers can use, in particular the cryptography can use. Okay, so that's the first part. The second part, okay, and that's actually an element that I put in the bag of science of security. So, if I were, as I said, I was speculating on what all things would go into a in the book of science of security, this would be one such thing. Here is a definition of what a programming language is trying to do, what an operating system is trying to do, what the computer architecture is designed to do, such that you can put them all together and get this idealized real world. Okay, so I think that's missing. By the way, I'm not an expert in any of these areas, so it's quite possible that there are things internal to these disciplines which try to do that, but the whole point is that they're not outside individual disciplines, right? A cryptographer doesn't know, what exactly is the operating system's model that we are getting that takes in, that, or rather, we know that it doesn't give us this model. So, yeah, that even if there is some effort towards going to that, we don't see. The second part, the complementary part, is that, okay, I was kind of putting it or like it's the ball is in the court of non-cryptographers, right? If you think of this is what cryptography is doing and this is all the other disciplines are doing, it's kind of saying, okay, you should all try hard and make it work for the cryptographer. But of course, I'm more reasonable than that. I would say no. Actually, there is some change that the cryptography model of real world will also have to make. Okay, so we'll have to live with something somewhat messy, quite possibly, right? It's probably not going to be as good as we were modeling it. And a good example for that is leakage. Okay, so there are all sorts of these side channels like timing or electric signals. They're low bandwidth leakage. So over the last, I don't know, 2 decades in theoretical cryptography, people started asking this question, can we live with this leakage? The reason is, you could ask the device designers to make sure there are no reckless, you know, signal leakage. The timing, you could have constant time circuits or constant time programs that compute on all data, spend the same time on all data. You have to maybe do something about your cache and so forth to achieve that. But so you can do a lot of things to minimize leakage, but it's rather unfair to expect that there will be no leakage. It will probably make the leakage very little, but what if there is an even little bit of a leakage, we are saying all bets are off. That's how cryptography is or has been. Okay, so what this new field of leakage Russellian cryptography proposed is, okay, let's actually meet them halfway and say that we will redesign our crypto systems, our encryption algorithms, signature algorithms, so that even if there is a little bit of leakage of maybe certain kinds of leakage, the key, some bits of the key are leaked or some limited amount of information about the key is leaked. We will still give you guarantee. The cryptography will give you that things are secure even if a little bit of the key is. But currently, that's not the case. If a little bit of the key is leaked, we say you're corrupt. You're not supposed to leak anything about the key. But leakage Russellian cryptography says even honest parties, non-corrupt parties, will be allowed to have a little bit of leakage. Okay? And this is, this was in the context of side channel attacks, but you could also imagine, things like maybe one of your subroutines is bad, right? The code is buggy. Can you handle that? And so, this is probably the more likely scenario that we would have, that cryptography also will have to be accommodating for a kind of a slightly messy real model and still try to give as ideal a model as we used to do. Okay? So this would be the kind of also something in the book of science of security. I will take another 5 minutes to kind of go on a slightly different route here. And that's, so we kind of went deeper in that stack of things I was showing you. Now I'd say actually there's also a case for going higher. Okay, so what do we do with this ideal? Okay, this ideal is like a, let's say an encryption. Think of it for now as an idealized encryption, right? So public key encryption. You could think of it as a channel. You could think of it as a black box. You can lock your message in. Whatever, some ideal model we are going to give to the give to who? Well, we'll give it to engineers who are going to use it and design higher level applications, right? So they build applications. They don't have to worry about all the cryptography inside it, all the circuits under it, the operating system, none of that, right? They can just use this model, the ideal model here, and build their applications on top of it. But there is a limit to how much they can just bank on the ideal nature of this. And this is what I was mentioning earlier. Say a secure channel, just because the channel is secure doesn't mean you cannot do anything bad with it, right? So for instance, maybe you're sending this message over a secure channel to a receiver who just turns around and puts this message out because that's what his or her app says. When you get a message, post it on Facebook. So so things could go wrong because of what the higher level application is doing. Maybe a bug in the application, maybe the design of the application, whatever, right? So you cannot quite just leave the these are, yeah, so the higher level application is not something the cryptographer is doing anything about, right? They say, look, that's not in our hands. All these, stack of things, programming languages, operating system, they all worked hard to give you this nice ideal primitives, channels and signatures and everything that you can use. Now it's up to you how you use them, okay? And unfortunately, these applications, if they are designed by, software engineers, right? Then there will be problems because these applications are not simple enough yet. And that's what really matters. You could actually have all sorts of, security here, but then if your application is leaking data, so if people are posting your, I don't know, Aadhaar data on the web page, well, there is no security breach or anything, but it's just that this person, copying this and pasting it there, shouldn't have done it, but they were following an application which made them do it, right? So it's not the fault of all the other, cryptographic system under it. Okay. So what really matters, once you have secured all this, there are a lot of good things you can do with it, but there are also a lot of dangerous things you can do with it. Okay. So the levels above this, we cannot just leave it for people to figure out by themselves. There is much more to it. There is a science to it, or there should be a science to it. Okay? So we'd like to formalize the functionality required of these very high-level applications. So think of something like digital payments or something like Aadhaar. There is no coherently stated functionality there. You have a bunch of laundry list of things you would like it to support, and then you would use the low-level tools like encryption and authentication to try and get to that functionality. But to begin with, that functionality itself is not formally specified. Unlike, here, the ideal world is very formally defined. And that's not true for our application. Sometimes, some of that is necessary because the ideal world is quite hairy, and you cannot, the higher level application is quite hairy, and you cannot put everything in place. So you have to move certain things into an environment which is outside the control of this ideal functionality, but you should still specify what this ideal functionality should do when it's interacting with the environment, right? What is the interface it has with the environment? That's what we do in here. We don't say what kind of messages will be sent through the channel, but we'll say, what to do when you get a message which is too long. You have to say you will not send it. So it's the same thing with designing these higher level applications. And once you have a specification, then you can worry about building it on top of these primitives. And most importantly, you can try to prove that this implementation that you have actually is a secure realization. Whatever can go wrong in your implementation using all these ideal primitives could have actually gone wrong even if you had this super ideal, say digital payments functionality. Of course, that means a lot of the difficulty is in designing this high-level application, high-level functionality, not the implementation, right? The functionality. What you want from an ideal digital payment, because whatever can go wrong there, you are not preventing that. So you should design your high-level application in a way that whatever can go wrong there, you are willing to live with it. And then once you have put that down, which may be not at all easy, then you can try to actually achieve it. Okay. And yeah, so one of the things here is that when you try to put down something, you might get something that's unachievable. Maybe because the way in which people interact, the order in which things are done in the real world, might put some restriction on what kind of functionalities are achievable. Okay? And so you might have to do multiple iterations before you get a primitive, get an ideal formulation that is even achievable, and then you can try to achieve it. Or it may be too weak, right? And you may not think of vulnerabilities when you're using that model, and you might want to add in additional safeguards even in that idea. Okay. The proof you might think would be the most complicated thing. I'm sure it will be complicated, but that's actually in some sense the most likely step that might simplify the most. In that, it could even be automatable. And there are tools, informal methods, which, if everything here is in this ideal world where you do not have cryptography going on, right, encryption going on, then it's conceivable that formal methods, model checkers and automated verification could all help in proving that this construction, some construction is secure. Okay, so that would be another thing to put into this science of security. I'm almost done, but there's one important thing that I will take one slide, and that is, we've been going up and down in that stack, but actually there's something even higher up, or you could say broader, and that's people. All the things that come with, when technology meets society. So we're building all this, fancy application with digital payment or, Aadhaar, and it's plugging into the society who wants to use it. And that affects society, people, institutions, everything is using these top level functionalities. They're designed in a way they can directly use so various kinds of functionalities, of course, or applications. Question is, the thing is, how people want to use it decides what it should be, right? What is the desired functionality? You could say, okay, if you don't have a smart card, you won't be given access to this resource, for instance. You could design something like that, but then you'll have some real social costs, right? A lot of people who don't have, cannot afford a smart card or a smartphone even, right? Won't be able to access your services, and maybe that's not good. So you might want to, that'll affect your decision on what functionality to implement and how to implement it. Okay, so the impact of your design of your functionality, including side effects that you had to do because of the, so you might have designed a nice ideal functionality to begin with, then you realize it's impossible to realize, you weakened it a little bit, so you have a bunch of side effects that you probably don't care about, but use might make a difference to the users, and costs and risks. So we design all this system, we don't often talk about what if things go wrong. I mean, there are errors that you can have a published paper with a bug in it. Your proofs can be wrong. So there is a certain amount of risk in translating from theory to practice, and of course that might be a big issue if it's going to affect people's lives. Okay, and it also is something that you cannot decide independently of the rest of the stack of things here. Some, the design choices go back and forth, right? You say, okay, this is not good for the people, let's change it. And then it will say, oh, this is not good for the design. You cannot do it this way without the side effect. Can we change it? So you'll need to kind of, your choices that you're making will affect both ways. And it brings into, with society comes all these, humanities, the bigger questions of ethics and user awareness, right? If people don't have a mental model of this functionality that they're interacting with, they may not use it correctly. Okay, so this is a little further off from the kind of science we talk about in cryptography or security, but this is also very much part of this science of security. Okay. So, to wrap up, what should the, so I hope I convinced you that there is a case for doing new things here to create a science of security, and what should the starting point be? In fact, what should be the starting point, right? First, I would say define it. Let's try to understand, what is the definitions. And once we have the definitions, we can worry about how to do it, because there might already be a lot of techniques for how to achieve various definitions. We just need to use the techniques correctly once we, so yeah, so a lot of things in this, talk, or everything has only been about the what part. The how part, I'm confident, once we figure out the what part, the science will take care of itself. That will be the how part. Okay, to summarize, this is my last slide. We had this very colorful picture of from the messy world. So this is kind of where the current cryptography is what it is doing, right? And then there are all these little other, they're not little, they're also big. In my picture, they are smaller because I don't know much about the details there. But all these other areas like programming languages, architecture, they also have their own silos, as it were, of treating the way they treat security, but they don't plug into each other. It's a very fragmented science. So it's not like there is no science of security. There are problems. There are many sciences of security, and what we need is a more comprehensive framework so that solutions at different levels would compose with each other, right? So it's one, science in which there's common terminology that goes across all these levels. Okay, and as I already said, the starting point would be the definitions. And how to do the definitions, we actually have several ways of doing it in cryptography. There's no one silver bullet. So it's not quite a solved problem, but we have a good handle of using the real ideal paradigm, various other things to give meaningful security definition. So there's a little bit of philosophical question also as to what is a good enough security definition, but that's something we know a lot about. And yeah, we need to bring people across different scientific communities, different disciplines, and so that they can talk to each other and understand that, okay, this is the common goal. They should have a common vocabulary to talk. Okay? So yeah, that's a long road ahead. That one of the things is to bring all these communities together itself is not very easy. We're all usually comfortable in our silos, and it's slow progress when you try to bring even two communities together. And here we are talking about several major disciplines within computer science and electrical engineering, and ethics and humanities. And so, right? So I think it's going to be a long road ahead, but not an impossible. Okay, so I'll stop with that. Thanks.
Yeah. So there are a couple of questions. I mean, it's a really beautiful talk, and you talk about the road, which I think everybody, like including cryptographers and the engineers and the developers should think about. And we have a couple of questions, if you can take.
Sure.
So there is one question: the encryption decryption used from long time. Is it possible to invent something new which replaces encryption decryption process for hiding data?
So it depends on what you mean by encryption decryption process. We certainly keep, inventing new things. So encryption today doesn't look anything like the encryption from centuries back, right? Or even a century back. So we have reinvented encryption decryption quite a bit. But instead of thinking of encryption decryption are like, you should think of them as means to an end. The end is this ideal world we have, secure communication. And yeah, there are, depending on the model in which you're living, if you're sending, if you have, now it's fashionable to talk about quantum channels, right? If you have a quantum infrastructure, quantum communication infrastructure, you could use, quantum key distribution or whatever the algorithms you want to do communication. It doesn't fundamentally change anything here. It's just that they're all different means, different ways to achieve this, the different means of, the different ends of secure communication. But I should say though that secure communication by itself is actually a simplistic goal, right? The problem, the complications come in when you plug it into, actually expand the scope of what your system is.
Yeah.
Everything is intertwined. What you're sending on, communicating with one person here, what you're reading on the news there, what you're seeing on the TV, they're all intertwined. So it's not, as you expand the scope of what you're considering as your system, things do get much more complicated than communication. So I don't know if I answered the question. The short answer is we have been reinventing things, both both the techniques and what we are trying to achieve using those techniques.
So there is one more question. Any alternative for RSA? So meant to say public key cryptography.
Of course, RSA is just, I mean, yeah, nothing super sacrosanct about RSA. In fact, the new TLS standards don't even really use RSA anymore. RSA was just one of the initial ways of doing public key cryptography, which became quite popular. It was convenient, it was easy to understand maybe, but it has its drawbacks. Some of its main drawback is one of its main drawbacks is its efficiency compared to elliptic curve cryptography, which is just another technique. And both elliptic curve cryptography and RSA are vulnerable to what are called quantum attacks using a quantum computer, which is not a realistic concern right now. But if it were to ever become a concern, then we do have other cryptographic systems using, for instance, lattice-based cryptography. These are called post-quantum cryptography. So yeah, we have a lot of ways of doing encryption. RSA is just one of them.
So rest of the comments are like great session, and they want to listen you more time. So that those are all questions. One more question is there. What are the PKI management system or tool?
What are the PKI management systems?
Or tools?
Or tools. So I've not at all touched on the the infrastructure of so PKI is a public key infrastructure, right? Not just the PKI infrastructure. There are many such infrastructures that we have not touched upon. Say you want to do internet security, right? There's a whole range of actors and its certificate authorities, and I mean they're all part of this PKI. It's a messy world. So that's maybe another mess I should have mentioned here. But it's a higher level mess. It's not at this kind of lower end, right? You could think of that mess as there's closer to that ideal or above that ideal in this picture, below, somewhere between that ideal plus and ideal, which tries to give you high level channel, like a secure communication infrastructure, including the internet, messaging channels and so forth. And it does have its drawback or limitations, right? So I'm not sure what the question is. There is a big, a whole lot of room for vulnerabilities and delicate difficulties, which are in the design of these higher level applications. They're not very high level. They're not at the level of something like, say, Aadhaar, but they're not at the level of encryption either, right? They're at this intermediate level where you're taking things like encryption, building protocols like TLS, BGP, and so forth, and trying to give a secure communication infrastructure. Maybe I'll say one thing about that here. The difficulty is not really currently, not because we don't have the crypto or we are not figured out the crypto there. The difficulty is also the legacy issues. So even to, or that's the first difficulty, right? So there is a protocol called BGP, which is used to figure out how to route my packets through the internet, right? It's all end-to-end encrypted, but I want to make sure my packets reach the other end and not get lost. Um, Unfortunately, BGP was designed in the good old days when everything in the internet was trustworthy or nice and honest players. So it's completely vulnerable to hijacking. Somebody can just steal your packets and not deliver them, change your routes, and so forth. So there is a notion called BGP-sec, which addresses some of the issues, or many of the commonly seen issues. I don't think anybody claims it's bulletproof, as in once you have BGP-sec, there will be new other issues. But our problem is not the issues with BGP-sec. Our problem currently is that the world has not been able to migrate from this obviously problematic BGP to an obviously better BGP-sec because of the hardware that is sitting around. They cannot handle encryption because of the vast legacy systems out there, right? So it has been transitioning from BGP to BGP-sec for so long, and so there are those kind of issues, right? Engineering issues, cost issues. Yeah, I mean, for science of security, I don't know how, they are real issues, right? They are for the application of the science, but they're probably short-lived issues. Short in the sense of maybe in a couple of decades we wouldn't be worrying about BGP or BGP-sec anymore. But in a couple of decades we would still be worrying about malware of one kind or the other, right? So in that sense, I think the science of security might be focused more on these gaps which have not been addressed. Things like BGP sec, where we have addressed it and it's just taking too long for people to adopt it. Yeah, that may not be where the big impact of the science of security as of now might be. I don't know, that is a kind of a wrapping answer to a short question, but PKI fits into this general question of, so PKI is used for in the internet for certificate authorities. And it's very important to make sure it's all good, and there are a bunch of protocols around it trying to make sure you're not able to misuse it. For instance, there is a DNS sec. But yeah, they have not yet been adopted. Not because we don't have the protocol, it's just engineering and economic issues.
Yeah, so thank you so much, Professor. Actually, I was chasing you for 1 year for your talk.
Oh, yeah, sorry.
So, but it's really great.
Finally,
so finally I got you, because I know you're very busy, and giving your time, it's really very important for us. So thank you so much for coming to Crypto Innovation
Thanks
Series.
a lot for giving me this opportunity also to think about these issues. It's only when you try to put it down that you actually get some clarity.
So it's really a beautiful talk, and I will definitely go for one more session with you. So whenever you are available and whenever it is possible. So thank you so much, and thank you so much, audience, for your response to Crypto Innovation Studies. We will come up with more such interesting sessions. So stay tuned for the next exciting part of the Crypto Innovation Series. Until next time, stay safe, stay secure. This is Shravani signing off. Thank you, Professor.